You want to know the future, not in some poetic way, not as a vague feeling, but the real future. What will happen exactly in detail, before it happens, because if the universe is a machine, then tomorrow should already be implicit in today. And the only thing separating you from prophecy should be ignorance and weak instruments and imperfect math. That's the story our intuition tells us every time we plan, every time we worry, every time we try to control what comes next. And it's the story classical physics seemed to promise for a long time. Newton gives you laws. You feed in the present. You crank the handle. And out comes the future, like a receipt from a cosmic cash register. In that old dream, you can imagine an intellect Laplace, this famous demon that knows the exact positions and velocities of all particles, and therefore knows the entire future and the entire past, with no uncertainty except human stupidity. But when you actually follow physics where it leads, the dream collapses, not because we are too dumb, but because the universe is not built to hand over the kind of information that perfect prediction requires. And Feynman's style of honesty, his refusal to pretend we know what we don't, forces you to face the disturbing answer. We can to predict the future perfectly because one, in many systems, the tiniest uncertainty in the present grows explosively until your forecast becomes meaningless. 2. Quantum mechanics puts a hard limit on how sharp the present can even be defined. And 3. Even if the future were determined in some deep sense, the computation and information needed to extract, it may be impossible for anything inside the universe to perform without changing the very thing it is trying to predict. Start with the first problem, because it's already fatal, and it doesn't need quantum weirdness. Chaos. People hear the word and think it means lawlessness, but chaos is what happens when the laws are perfectly precise and the world is still unpredictable, because the mapping from now to later is so sensitive that microscopic differences get amplified into macroscopic consequences. The weather is the classic example. The atmosphere obeys fluid dynamics and thermodynamics, and those laws aren't vague. They're not mystical. They're equations you can write down, but the air is a gigantic nonlinear system, and in nonlinear systems, errors don't just add, they multiply. Your measurement is off by 0.001% here, a thermal fluctuation there, a rounding error in a computer somewhere, and a few days later, the forecast diverges into a different world. This isn't because the atmosphere is random. It's because it has a precision amplifier. It takes tiny uncertainties and inflates them until your future becomes a cloud of possibilities. You can see the same phenomenon in a double pendulum, in turbulence, in populations, in the three-body problem, in the drip of a faucet, deterministic equations, unpredictable outcomes after enough time. Because to predict perfectly, you'd need to know the present with infinite precision. And infinite precision is not a thing you can buy with better instruments. It's a mathematical fantasy. You might say, fine, then that's just a practical limitation. If we had absurdly perfect measurements, we'd win. But physics doesn't let you cash that check, because the second problem is not practical. It's principled. The universe does not contain, in an accessible way, the classical complete present your demon needs. Quantum mechanics arrives, and it does something brutal to the concept of a fully specified state. It tells you that certain kinds of exactness are not merely unknown but not simultaneously definable the way classical intuition demands. Uncertainty principle is often taught like a story about disturbance measure position, and you kick the particle. So now you don't know momentum, but the deeper point, the one that survives even in the most careful formulations, is that the theory does not assign arbitrarily sharp joint values to all the classical variables at once. The present in quantum physics is not a list of exact positions, and velocities waiting to be read off if you build a good enough microscope. So chaos says you need perfect initial conditions to predict far into the future. And quantum mechanics says perfect initial conditions are not something nature offers in the form you require. And then quantum mechanics turns the knife by showing that in many cases prediction is So chaos says you need perfect initial conditions to predict far into the future. And quantum mechanics says perfect initial conditions are not something nature offers in the form you require. And then quantum mechanics turns the knife by showing that in many cases prediction is not even a matter of incomplete knowledge, but of probability. Radioactive decay is the cleanest example because it refuses every classical story you want to tell. Give me a uranium atom, and I can tell you the half-life. I can tell you how many atoms in a kilogram will likely decay this week. I can predict statistics with eerie accuracy. But which particular atom decays at 3 hours 7 minutes and 12 seconds, and which one waits until 3 hours 7 minutes and 13 seconds? Quantum mechanics does not give you a hidden schedule that you simply haven't discovered yet. It gives you a probability per unit time. And you can argue interpretations all day people do, but the operational content that Feynman cared about is that the theory as output is a distribution of outcomes, not a single guaranteed event. That's already the death of perfect prediction, because perfect prediction means one future, not a spread. Now combine the two problems and you get something that should genuinely unsettle you. Chaos amplifies tiny differences, and quantum mechanics guarantees that at some level there are irreducible tiny differences. Even if quantum randomness usually averages out in everyday objects, there are systems perched on the edge of instability, where microscopic fluctuations can decide macroscopic outcomes. Which droplet forms first, which spark becomes a lightning channel, which neuron reaches threshold first in a noisy brain, which path a chemical reaction takes when multiple routes are available. You don't need to claim silly cartoons like one quantum event causes a hurricane to see the real point. There exist chaotic systems whose long-term behavior depends on details that cannot be specified with infinite sharpness, and therefore their future cannot be nailed down as a single trajectory, even in principle. And if that were the whole story, it would already be enough. The future is not perfectly predictable because the present is, not perfectly knowable, and small uncertainties get magnified. But physics adds a third layer that is quieter and in some ways even colder, because it says that even if the universe were deterministic, and even if you somehow had the information, you might still not be able to compute the future faster than the universe computes itself. There is a difference between the laws fix what will happen, and an observer can efficiently calculate what will happen. Some systems are computationally explosive. To predict them exactly, you must perform a calculation whose complexity grows so fast with system size that no machine made of matter obeying the same physical limits can complete it in time. You can imagine trying to forecast the exact molecular configuration of the air in this room 1 minute from now. The equations exist, but the information content is astronomical, and the computation required is so vast that the universe will have evolved before your prediction finishes. This is why, even in classical statistical mechanics, we don't predict microstates. We predict distributions, averages, pressures, temperatures, flows-coarse-grained realities that are stable under ignorance, because the microscopic future is a combinatorial monster. Feynman saw a version of this problem in quantum mechanics in an especially sharp way. This state of a quantum system with many particles lives in a space whose description grows exponentially with the number of parts. And that means simulating quantum physics with a classical computer becomes hopelessly expensive as the system grows. Nature seems to keep track of its own evolution without effort, but that doesn't mean you can compress that evolution into a cheap calculation. It may be that the universe is lawful, yet computationally irreducible, so that the only way to know the exact outcome is to let the physical process run. And then, just when you think you've found a way to cheat copy the present, simulate the copy, keep the original untouched quantum theory, puts up a sign that simply says nitrogen monoxide. You cannot, in general, make a perfect copy of an unknown quantum state. The no-cloning theorem isn't philosophy. It's mathematics inside the theory, and its implication is devastating for the fantasy of perfect forecasting. A perfect predictor would like to take the exact state of the world at this moment, duplicate it into a sandbox, and compute forward without disturbing reality. But quantum mechanics says you can't just photocopy the full physical state of an arbitrary system. And measurement doesn't rescue you, because measurement doesn't reveal a complete hidden classical description. It yields outcomes with statistical structure. So now the trap is complete. Chaos says you need perfect knowledge of the present. Quantum mechanics says the present cannot be specified with infinite classical precision, and some events are intrinsically probabilistic. Computational complexity says even with knowledge, you may not be able to crunch the result. And quantum information says you can't necessarily copy the present to simulate it without disturbance. At this point, people often try one last escape. But surely the universe itself has the information. Surely it knows what will happen. That sentence contains a hidden mistake. The universe doesn't know anything. It evolves. And you, who want the forecast, are not outside the universe reading a log file. You are inside it, made of the same matter, limited by the same speed of light, the same thermodynamic noise, the same quantum rules. Even relativity quietly participates in the limit to predict what will happen in a faraway region right now. You would need information that cannot reach you faster than light. And beyond cosmic horizons, there are regions you can never receive signals from at all. So even the very idea of a complete global present accessible to one predictor is physically suspect. That's the disturbing answer in its most honest form. Perfect prediction requires a God's eye view, an infinite precision and infinite computation, and non-invasive access to realities as full state. And physics provides none of those. What physics does provide beautifully, powerfully, is something different. Predictability in the ways that matter. It gives you reliable patterns and stable laws at the scales where small uncertainties wash out rather than explode. It gives you thermodynamics, where you can track molecules, but you can predict pressure and temperature with ruthless accuracy because the details average out. It gives you engineering, where you can build bridges and circuits because the collective behavior is robust. It gives you weather forecasting for days, sometimes weeks, because chaos needs time to amplify errors. It gives you quantum mechanics, which is probabilistic, but so precise in its probabilities that we can build lasers, and semiconductors and MRI machines and atomic clocks. So the lesson is not, the future is unknowable. The lesson is sharper and more unsettling. The future is only partly compressible into knowledge. Some futures are tight and predictable. Some are distributions. Some are fog beyond a horizon of chaos. And some are in principle inaccessible because the information needed to specify them is not something you can extract, copy, or compute without limits. And when you really absorb that, you see why Feynman's attitude matters. He didn't sell fake certainty. He loved the fact that nature is deeper than our demands. We can predict an eclipse centuries ahead because gravity in that regime is stable and the relevant variables are accessible. We can predict the exact path of every molecule in a flame because that is a chaotic, noisy, information-rich system where the microscopic details are both inaccessible and irrelevant. And when you ask, why can't we predict the future? The most disturbing part is not that we're missing a clever trick. It's that the universe seems to be built so that complete prophecy is not a physical operation available to anything inside it. The future is not a book already printed that you simply haven't opened. It's a structure of possibilities constrained by law, narrowed by information, and realized by the unfolding of processes that sometimes amplify ignorance and sometimes generate outcomes that no amount of classical knowing can pin down in advance. That can feel terrifying because it denies you total control. But it can also feel strangely liberating because it means the world isn't a script you could have read before you lived it. Physics doesn't give you omniscience. It gives you something more honest, a map of what can be predicted, what must be treated statistically, what becomes chaotic. The universe allows prediction, yes, but it does not grant prophecy. And once you understand why, you stop blaming your brain for not being a god, and you start seeing prediction for what it really is. A hard-won local success inside a reality that is lawful, deep, and not obligated to be fully knowable from within.